Hello, I'm Dr. Pierce Von Lockett, and I'll be talking to today just a couple of slides about how to apply symmetry in different problems, and specifically with how to apply symmetry in this plate with a hole problem. So we're going to talk about symmetry. Hopefully you'll understand symmetry about plate with a hole and then can apply that to other types of problems that you might see. How do we go about identifying planes in symmetry? That's something hopefully you'll be able to do after this lecture. And how to look at applying appropriate boundary conditions to a symmetric model. Should they be fixed? Should they be rollers? Hint, they should be rollers to recreate the response of the full model. So for linear static analysis, designs with symmetric features can be reduced to expedite the analysis. They allow us to analyze a smaller section of the whole part. And since we're analyzing a smaller section of the whole part for the same number of elements, meaning the same size of our computational problem, we can actually have a higher element density, more elements per unit area, and that'll give us a better result. As we see in this problem, we have two planes of symmetry. We have a vertical plane, we have a horizontal plane. We can cut this into a quarter, and since we can cut this into a quarter, we can analyze just a quarter of it, and from this understand that, yeah, if we pull on the right, if we pull on the left, and our loading is symmetric, then what we would expect to have is that the top and the bottom would behave the same, and the left and the right would behave the same, such that all we need is to model one quadrant. How do we go about doing this? Well, if we look at the geometry of the model and look at the geometry of that one quadrant, and we understand that, well, the top and what would be on the bottom and the top right and what would be on the left should behave the same, that center line, vertical, should not actually move. It's just going to get pulled apart from the center. And here, the center line shouldn't move. Whatever happens on the top happens on the bottom, such that nothing should move through this plane, and that plane then therefore cannot warp at all. A couple of things to consider. Just be sure that when you are looking at the symmetry of the geometry, you also need symmetry of the loading. Like I said, this one's loaded on the left and on the right, and it's normal to the surfaces, so everything's good there. And also, the symmetry may not apply to symmetric responses in a dynamic analysis like they do in a linear analysis or in a buckling analysis. So in this standard static linear analysis, we kind of know what the deformed shape is going to look like. We know it's going to be symmetric with respect to these horizontal and vertical planes, such that we can apply these without a lot of problem or issue. We do this, in this case, with roller constraints because we expect that, yeah, this plane can't move to the right, but it may move up and down. The same thing here. This plane can't move to the left. I'm sorry, it can't move off the surface, but it may move left and right as it expands or contracts. So we have to account for that, and rollers do a good job. All right, so that's all I have on that one. Please, as you go through the application packet, the tutorial for this plate with the hole in the next lecture, take care to think about all the stuff that you're applying. These boundary conditions, we're applying a model, it's a linear model, so the model itself for the material doesn't actually apply any stress concentrations, but the geometry of the hole does. And then as we're creating that whole geometry, we can calculate what that analytical solution should go to, and we want to actually then make check out what the simulation does to see how they compare. That's going to be the ultimate goal. Okay, thanks for participating. Hopefully you've learned a little bit about symmetries, and if you think about how to apply symmetries to other geometries, that'll help you with the homework as well. Take care. See you in the next lecture.